Here's our last set of rocks, metamorphic rocks. These notes are intended to give you some background so that you can easily recognize and classify metamorphic rocks. Here's a great example of metamorphism. If you were to look at an outcrop and see this, you would see that the veins of quartz have obviously been distorted. So pressure has squeezed this, what normally should be a straight, kind of more linear vein of quartz, into this S shape. And here again is another example of that same kind of pressure that creates this kind of zigzag shape within rocks. You can see the quartz, which is the light colored, and the darker mafic, plagioclase feldspars probably, and biotite and hornblende are all squeezed together to make this kind of zigzag pattern that is pretty obvious of metamorphic rocks. High temperatures originate from the Earth's internal heat, but the high temperatures can also come from these hot igneous intrusions that help to bake or cook or alter the rocks that surround it. Here's an example, it's a good graphic showing what's called contact metamorphism. When you have an igneous intrusion, you've got very high temperatures of this magma that intrudes pre-existing rocks. In this case, the pre-existing rocks are layers of sedimentary rock. And this zone on the outside here, where the magma is adjacent to the sedimentary rocks, is an area where those minerals within the sedimentary rock are going to get altered and cooked and kind of baked, so they undergo what's called contact metamorphism. High pressures can come from either overlying rocks, so just the weight and the pressure from rocks laying on top, but also from compressive forces as a result of mountain building and the movement of tectonic plates. Here's a good photograph of clearly a chunk of rock. This is an outcrop right off of a highway, and you can see what normally should be flat or horizontal lying layers of rock have been folded up into this kind of V shape, and clearly compressive forces were involved here. So remember that metamorphism is that process by which the texture and the composition is changed, it's altered, but it's done so without actual melting of the material. If there's melting of the rock, complete melting of the rock material, then it's basically rendered a magma, and then that type of rock would then be igneous, not necessarily metamorphism. So metamorphism is altering but without complete melting. There are three general types of metamorphism I'm going to want you to know about. The first is regional metamorphism. So we're talking very large sections of the Earth's crust, and usually we're talking about on the order of square kilometers in area that are affected. Here's an example of a large area. This is a quarry in Italy that is being mined for marble, a very pure variety of marble known as Carrara marble used by sculptors. And the next picture you'll see the David, which was carved by Michelangelo from this quarry that was formed by regional metamorphism of limestone to form marble. Here is a photograph of the famous David sculpture, sculpted from one large piece of Carrara marble by Michelangelo. An amazing sculpture, an amazing pure variety of marble that was used. Contact metamorphism is molten rock from an igneous intrusion that affects a very localized area, as in the diagram I showed you before with the intrusion that cooks or bakes the layers right around it. This type of metamorphism is localized, so it only covers and only affects a pretty small area. Hydrothermal, when you break down the word hydrothermal, we're talking about hot water, and it is hydrothermal is hot water metamorphism, so it's actual alteration of minerals within a rock by means of the heated water. Actinolite is a mineral that actually derives from, is formed from the alteration of magnesium-rich minerals within a rock, and hydrothermal or hot water intrusions and hot water seeping through the rocks can change the nature of the minerals. two textures you'll be classifying, foliated and non-foliated. Non-foliated are going to be rather blocky and they look rather homogeneous, so you're not going to see obvious banding. You might see some evidence of lines or waves, but it's generally going to be fairly blocky. Here's serpentine, the California state rock. This is a good example of a non-foliated rock, metamorphic rock, and the green comes from magnesium silicates that are altered in the process of metamorphism. Foliated means you can actually see wavy, the layering of minerals, parallel banding of minerals, and the orientation of the grains is obvious. It is perpendicular to the direction that the pressure was applied. So you can imagine that the mineral grains are actually literally squeezed out opposite of the direction of pressure. All right, now we're ready to look at some metamorphic rocks, classify them, and get used to some rocks in our kits so that we can do a great job on our rock identification lab quiz. Good luck.